Good morning, gentlemen. Happy Wednesday, April the 1st. Today we are going to continue our discussion of electricity by talking about something called electric potential. Now, we've talked about potential energy in a variety of different ways. We talked about gravitational potential energy, we talked about elastic potential energy, and so we want to continue that discussion today. All right, and so lesson 75 is all about elastic potential. Now, what is electric potential energy? Well, let's talk a little bit about what gravitational potential energy is. Let's say we're sitting here. This is the ground, and I put a ball or a rock or something like that on the ground. Right now it's got 0 joules of potential energy. Well, if I do work on this ball and I lift it up and I put it somewhere here, now I've given it gravitational potential energy. Okay, it doesn't want to be here. It has the potential to fall back down. The same kind of thing is true in terms of an electric charge. Let's say I have a big old point charge that's negative, and I have a teeny weeny little positive test charge next to it. Okay, if I take this positive test charge and I push it this way and I put it somewhere out here, all right, it now has the potential to but move back toward the negative charge that you see over here. This is the same concept that we're dealing with gravity. All right, the positive test charge over here doesn't want to be over here. It wants to be where the negative charge is. So by doing work on it and pushing it over this way, I've given it electric potential. So by definition, the electric potential at any point in an electric field is the work required to bring a unit positive charge from anywhere to that point. How much work do I do? Now, keep in mind also that if the point charge is positive, then the positive test charge wants to be out here. All right, and so you'd have to push it in order to get it closer. But the moral of the story is that when a charge is moved, work is done, and the potential energy of the charge is changed. All right. Now, interestingly enough, the difference in potential energy is called the potential difference or voltage. All right. And that's the difference in the potential energy from, from this point here to this point here. So this difference, right, there's a potential energy here, and there's a different potential energy here. All right, and so the difference between those 2 points is voltage. Okay. It's tough writing with a mouse. All right, so what do we do with this information? What exactly is electric potential? Well, of course, you're certainly well aware that the difference in potential energy is called the voltage, right? We just talked about this. But mathematically, it is defined by the formula V for voltage equals W for work over Q for charge, all right? Because think about it. You're doing work on a charge to give it potential energy, all right? So voltage is the amount of work that you've done per unit charge, all right? So that's the definition of voltage. Now, 1 joule of work moving 1 coulomb of charge is a volt. All right. Now, this gets a little weird because a volt is the unit of electric potential. Voltage is the definition of electric potential. All right, and they both are symbolized with a V. All right, so both the variable and the unit in this case are V's. All right, that's a little weird. By the way, the formula that you see here is found on the electricity page of your handy dandy New York State reference tables. So have a look at that. Make sure you know where it is and how to use it for Friday's quiz. Last thing that I want to point out here is this, an electron volt. Now, an electron volt, by definition, is not a unit of voltage. It's not the same thing. It is the energy or the amount of work that is required to move one elementary charge, in other words, a proton or an electron, through 1 volt of potential. All right. In other words, how much voltage does it take to move an electron? All right. Think about that. Electron volt. Okay. It's an odd name and it's bothersome because many students will get confused with it. But electron volts, well, let's start with volts. Volts are a unit of potential energy or potential difference. Electron volts are units of work, essentially, the energy required to move 1 elementary charge through 1 volt of potential. It turns out that 1 electron volt is equivalent to 1.60 times 10 to the negative 19th joules. Okay, now that number, 1.60 times 10 to the negative 19th, that is the amount of charge in 1 electron, the charge in one or on 1 proton. All right, so the numbers are similar. 1.60 times 10 to the negative 19th joules is the charge. 1.60 times 10 to the negative 19th electron volts is the amount of energy required to move that charge through 1 volt of potential. Now, this brings us to example number 4. What work is done when 5 coulombs is raised to potential by 1.50 volts? All right, so we'll have a look at this, and of course, we always start by making ourselves a laundry list. And so example number 4 starts with the question, how much work is done? So W is going to be my big fat question mark in this case. Now, we have a, come on, why isn't it popping up? There we go. The charge is 5.00 coulombs, and the voltage is 1.50 volts. Okay, so we've got work, we've got charge, we've got voltage. Now, of course, we know that the formula for all of this for voltage is going to be V equals W over Q. And so we write this down. In this case, we are going to have to algebraically rearrange it. So W is going to equal V times Q. So 1.50 coulombs, I'm sorry, 1.50 volts times 5.00 coulombs gives me 7.50 volt coulombs. But again, this is work that we're solving for. And so the unit volt coulomb is equivalent to a joule. Okay. Now, in terms of electric potential, there are some other issues or other formulas that we can derive using this information. Whoa, that surprised me. So we'll start with the formula we just derived. All right, we've got voltage equals work per coulomb. Whoops. But we know that work, what the heck is going on? Work is equal to force times displacement. And so this new mouse is really starting to annoy me. Sorry. So work is equal to force times displacement. So in this case, I can say that voltage is going to equal force times displacement over charge. But I also know that force over charge is the electric field intensity. And so I can take this term here, F times D, force times displacement times Q and set it equal to ED. All right, ED. So voltage is also equal to E times D, electric field intensity times displacement. Now this formula is not found on your handy dandy reference tables, so I suggest that you write it down on your reference tables. Okay, that brings me to example number 5 in this case. So let's have a look at that. The electric field intensity between two charged metal plates is 8.00 times 10 to the 3rd newtons per coulomb. The plates are 0.050 meters apart. What, pray tell, is the potential difference between them? So let's have a look. Again, we always start with a laundry list. So in this case, we know that the electric field intensity is 8.00 times 10 to the 3rd newtons per coulombs. All right, so we'll start there. Then, next one, the displacement is equal to 0.050 meters. And of course, my big fat question mark is the voltage that we're looking for. Well, do we have a formula that includes E and D and V? Well, of course, the answer is yes. All right, we just derived it in the previous slide. So for this one, no algebraic rearrangement is required. So V equals E times D. 8,000 newtons per coulomb times 0.050 meters is equivalent to 400 newton meters per coulomb. All right. And notice that I wrote it in scientific notation because we can only have 2 significant figures in our answer. The other thing that you should realize is that a newton meter per coulomb is equivalent to a volt. Okay. Your homework for tonight, gentlemen, is on the electricity worksheet to do questions 5 through 7. Now, I'm going to change up. This is April 1st now. I'm going to change up the assignment. I'd like you to actually take a picture of your work and email it to me by tomorrow. Okay? Thank you very much and have a great day.